Morning, everyone. So we've reached the end of our second big chapter. This one here has been a chapter on dynamic equilibrium. I was thinking of just summarizing some of the main key concepts, just to make sure that we've hit everything, see if there's any questions, and then we'll practice more problems from the worksheets. So we're going to start off here. This unit here has been on, in chemistry, we deal with dynamic equilibrium. They always like asking you, what does it mean, dynamic equilibrium? Equilibrium here, we always think in our, just back in the mind here, equilibrium means I hit some sort of balance. In this case here, equilibrium, what you can say is macroscopically, when I look outwardly, all the properties I can see actually look like they don't change. Macroscopically, properties are constant in time, right? So it's like the chemical, like when I know the concentrations, they just stay fixed in time. However, even though outwardly it looks like nothing's changing here, in chemistry, all of our equilibrium systems are dynamic. Dynamic still implies things are moving, things are actually happening. In this case here, although that's happening macroscopically, microscopically here, our reactions continue to occur. So microscopically, our reactions continue to occur. Again, we talked about here, how can these both be true? How can it be that reactants are becoming products and products are becoming reactants, and yet outwardly nothing changes? The way we actually wrap those two things together was we concluded whatever your reaction is, the forward rate, the speed at which reactants become products, has to have equaled the reverse rate. So that way we can still have changes, we can still have reactants becoming products, products becoming reactants, but as long as, like in the hockey game analogy, 3 players jump off and 3 players come on at exactly the same time, we're going to still stay overall in balance. We started off this unit here looking at only some reactions will end up reaching equilibrium. How do we decide which ones will reach equilibrium? So we looked at a quick section here on spontaneity. For spontaneity, there were 2 factors that were involved. One factor here was enthalpy. Enthalpy is sort of measuring the heat energy in the system here. If nature had its way, nature prefers to go to minimum enthalpy. The lower the energy, the more stable. So in that case there, again, nature prefers minimum because it actually refers to it being more stable. In this case here, the minimum enthalpy side, it's going to point towards, I can say towards the exothermic direction, or simply here you can say points towards the heat term. In that direction, you're pointing towards the side which has less energy, you're pointing towards the side that has more stability, right? That's only half the story though. The other half of the story here was a guy called entropy. Although entropy, somewhere along the way, entropy does have to do with energy, we just think of entropy as a sort of a measure of chaos. And if nature had its way, nature prefers to maximize entropy. Things naturally become more chaotic, more random, more disorderly, rather than ordered. So for this one here, how do you decide which one is maximum entropy? We want to look for which side has more moles of the most random phase. And we had a relative ordering of these phases here. Solids are nice and ordered to pack, so liquids are going to be better than it. Mixtures are always going to be more chaotic than a pure sample. And then we have gases spreading out through the rest of the container here. That one definitely will be the highest entropy, right? So let's just do as a quick example here. Let's look at ethane, so C2H2. This one here is a gas. This is reacting with 2Cl2 as a gas. This one here is going to become C2H2 Cl4. Basically, I added the chlorines on there. This one here, let's say it comes out as a liquid. And I'm actually going to give you that the delta H is negative 386 kilojoules. Okay? So I'm going to ask it this way here. Will this system reach equilibrium? Will it go to completion, or will it go 0%? First problem here is our heat term is separated off as a delta H. Because I know a negative delta H is exo, I can put this heat term back in. I can actually put it in as a positive plus 386 kilojoules, right? And now I can do my trends here. For enthalpy, I want to minimize enthalpy. I want to point towards the heat term. Minimum enthalpy, I want to go to products. That's how it's more stable. But what about the maximum entropy argument? Maximum entropy wants to look for the most random phase. The most random phase is actually gas on the left side. It's liquid on the right side. The maximum entropy actually is on the left side. So in this case here, I want to go forwards because that side's more stable. But I actually want to stay on this side because it's more disordered. So in that case there, we're going to end up hitting some compromise. This system here will end up overall reaching equilibrium, although it will take a little bit of time to actually get there. Let's do one more here. So let's take CH4 as a gas. Let's become O2 as a gas. This one is supposed to become CO2 as a gas and 2 water as a liquid. This is a combustion, so it's really, really exothermic, 394 kilojoules. The question here is worded a little bit strangely. I want you to actually tell me, describe what happens to enthalpy and entropy, and what they're going to do is they're going to force a direction on you. So entropy for, let's do the reverse reaction just for practice. Right? So I could do the same thing. I could do which side is the lower energy side? Minimum enthalpy is going to be to the right, it's towards the heat term. Which side is more entropic? Well, we have gas on this side, we have gas on this side, gas, right? Oh, I have more gas on this side here. I could say maximum entropy is going this way, but this time what they're asking is they're saying just for the reverse reaction, just for looking at these guys here going to the left side. I realize I'm missing a 2 here. Just for going to the left side here, what happens to the enthalpy, what happens to the entropy? Entropy is the easier one. Well, maximum entropy, right? Reverse direction, perfect. You go from 1 gas to become 3 gases, the entropy increases. That's what nature wants to do by going in the reverse direction. However, what happens to the energy? Well, in this case here, our potential energy diagram here says we actually start high and we actually end low. In that case there, we're minimum enthalpy. Nature wants to go towards the right side, but as I go left to right, as I go right to left here for the reverse reaction, the enthalpy actually increases. That's actually not what nature wants to do, but they've actually forced a direction on you to actually describe it. So that's the way we're going to do it. So in that case there, we'll also end up hitting a situation of equilibrium. Right? So that was just sort of our first look in this chapter here. We wanted to decide which systems end up reaching equilibrium, which ones go 100%. If both factors are against you, both factors want to keep you on your side, you're actually going to go 0%. Right? Next, what we did is we skipped forward and we said, okay, now assuming the system has reached equilibrium, we now poke at the system with Le Chatelier's principle. Make sure you are able to state Le Chatelier's principle. Even though we've sort of summarized it, oh yeah, nature just hates what we do. It tries to undo what we do here. That's just sort of a nice memory aid for you. You still need to mention a couple things. When a system, you can say closed system, at equilibrium. So it's important for you to note we are already at equilibrium. Before I reach equilibrium, don't even worry about Le Chatelier. Okay? When a system at equilibrium is stressed, we poke at it somehow. I change the temperature, I change the pressure, the volume, somehow. Nature tends, what does it do? Nature tends to counteract the stress. Right? So it's not that nature prefers things to be cold or hot or whatever. It just hates what we do. A couple features here is, yes, we are poking at an equilibrium system. There is this whole notion of tending. It tries to. It never really gets backed up to what it needs to be, but the direction is definitely going against us. Right? So let's just have a look at an equation here. Let's take 4 gold as a solid. It reacts with 3 oxygen as a gas. Endothermic reaction, equilibrium with 2 gold 3 oxide, also as a solid. I don't need to worry about the spontaneity argument. They've already said this is going to be entropy. This is going to be equilibrium. What I'm going to do is I'm going to give you a few different stresses. So let's do this by a table just for simplicity here. How do you want to poke at the system? So in part A here, my stress is I want to increase temperature. If I heat things up, which way is it going to shift to? Part B, I'm going to remove oxygen, remove O2. What happens to it? Part C, I want to increase, actually let's do decrease. Decrease the pressure. I want to add a catalyst. Okay. They can ask this in many different questions. Just for simplicity, I'm asking all at once. A tricky one here. What if I add AU2O3 and the hint there is solid? Okay. So in this case here, that's how I'm poking at the system. we talk about Le Chatelier as trying to respond, as trying to go against you. So we're dealing with the shift, and I'm just going to make a list of sort of what are your consequences, what happens to the concentrations as that shift happens. So as I increase temperature, yes, what happens is you end up heating the entire box. But the easy way to figure out the answer is think about the heat term as actually a chemical itself. I have increased the heat term. Nature doesn't like that. It's going to try to get rid of that shift there. So in this case here, we're going to end up shifting right, or you can say shift towards products. As you shift towards products, I should lose reactants and gain products. So my oxygen amount here should decrease, and I should end up with having more Au2O3. If I remove oxygen, so sort of the opposite here, we had an equilibrium system, I pull down the oxygen. Nature doesn't like the fact of losing so much oxygen, it's going to end up shifting left. So shift left, and again, what happens to the oxygen then? Well, a couple things. That one's a little bit more complicated here. If I plotted concentration versus time, I start off with the oxygen, fine as it is, it's equilibrium, it's constant in time. I remove the O2 all of a sudden, so there's a steep decrease there. As I shift to the left and regenerate some of the oxygen, the O2 climbs, but then it never ends up reaching as high as it was to begin with. So I would say here overall, compared to the initial equilibrium, the O2 has decreased, and again, maybe it makes more sense in words here. The O2 is less than the initial equilibrium. Right? What if I decrease pressure? Now, I always think of pressure, yes, it's affecting gases, but pressure and volume are inverses. So what if I suddenly give you much, much more room to sit in? In this case here, with the more room, I have only a solid filling up the room on the right-hand side here. I do have gases here. If I suddenly go from a container, small container to a big container, I want to shift to the left, produce more oxygen, and therefore I can end up filling up that room a little bit better. So while, again, there would be a steep decrease at the moment that you increase the container, over time the oxygen is going to climb. If I wanted to sketch that graph there, concentration versus time again, we start off, the concentration of oxygen was perfectly fine. As I suddenly increase the volume, because C is equal to N over V, the volume goes way up, the concentration goes way down. So suddenly the concentration of oxygen goes way down, but as I start shifting to the left, as I start gaining more oxygen, the oxygen steadily climbs back up. Again, it's nowhere near as high as it was to begin with, so you can say overall, again, compared to the original equilibrium, the oxygen has decreased. Okay. If you add a catalyst, you've actually lowered the activation barrier for both the forward and the reverse direction, so therefore there is no overall shift, so there's no shift. I wanted to sort of throw in a quick little twist here. What if I add Au2O3? And why have I just been looking at O2? The thing I want to emphasize here is you'll notice the Au2O3 and the Au are both solids. These ones here are incompressible. Not only are they not going to interact with pressure and volume just like gases would, what I want to be really clear here is because they are solid, solids have a constant concentration. And usually they word that they have a constant composition, they have a constant density. So it's a little bit weird to think about, what do you mean concentration of solid? Well, for a solid, I already have my amount of room I'm taking up. I can figure out how many moles worth of particles. It's sort of like the number of particles divided by how much room the solid itself is taking up. I can definitely have more solid. So that's what I'm doing in step E here. I'm going to toss in more Au2O3. However, have I actually shifted the equilibrium? Well, sure, I've added in more particles, but I've also added in like sort of more volume that the space is actually taking up. By the time I actually work the ratio, sort of like a density here, the amount of moles divided by the space I've taken up, I have twice the number of moles, but it's taking up twice the volume, 3 times the moles, taking up 3 times the volume. I definitely have more solid, but the concentration actually doesn't change. So let me just write that down in words for you here. Keep that in mind. We may actually have more solid in the system, more solid added, but if I use this phrase here, the concentration of solid doesn't change. And this is going to become important in our next chapter. The concentration of solid doesn't change, which is why we can ignore it in our KEQ expression. If there is no change in the concentration, even though I'm adding Au2O3, it doesn't suddenly, oh, this goes up and then I shift to the left. I'm not actually able to change the concentration. I have more of it, definitely, but because that fraction, that ratio there hasn't changed, there actually would be no shift, just like in the adding catalyst case, right? So just watch out for that. We sort of captured that a little bit here when we started looking at KEQ. So KEQ, just introduced a little bit of the math here. KEQ was this equilibrium constant. And basically KEQ was defined as a ratio of products divided by reactants. Even though our reactions are reversible, we still generically say reactants are becoming products, right? We still say reactants on the left, products on the right. And KEQ essentially is just a general measure, well, roughly how many products do I have in comparison to the reactants. If this K value is bigger than 1, that means my fraction, right, products over reactants, for a fraction to be bigger than 1, I have way more products, less reactants. That means at equilibrium, I have more products. Products are favored. If the K is less than 1, yes, it can't drop below 0. For a fraction here to be lower than 1, that means this product over reactant ratio here, that means I have less products, more reactants. I can say reactants are favored. That's another language for it. Reactants are favored there. And if K is equal to 1 here, we have roughly products about the same as reactants. You have to be careful, especially if we have coefficients in our balance equation. Sometimes those coefficients, as they enter into the powers, sometimes it makes this expression not quite true. So let me do a quick example of that here. Let's do oxygen as a gas is converting itself into ozone as a gas. So I do the balancing here, 3 oxygen, 2 ozone as a gas here. First thing they can ask you is state the KEQ expression. So if I did a product over reactant for this guy, what would it look like? Well, the products in this case here is O3. So we have our O3. There is, the numbers go up into the power, so O3 squared, multiply it by O2 cubed. Sometimes for a multiple choice question, they try to sneak in just to confuse you. Oh, there's a 3 oxygen. Sometimes they try to squeak in that 3 there. In general, there should never be a number inside that square bracket. You can make a note to yourself here. The coefficients become powers, right? And if I have many different chemicals here, everything just multiplies, right? So coefficients become powers. A couple other side notes here is KEQ is, well, we talked about the number. KEQ is dimensionless, so it has no units. KEQ is only changes with temperature. So as long as we're under the same temperature, as long as between part A and part B of the problem, temperature doesn't change. So therefore, we are exactly the same. Constant. So this constant tells us roughly, even though we're at equilibrium, remember while we're at equilibrium, so at equilibrium, concentrations are constant in time, right? Macroscopically, nothing changes. However, usually, concentration of products does not equal concentration of reactants. It's like that hockey game. At any given time, I should have 5 players on the ice, but it doesn't mean, oh, just 5 players on the ice has to mean you have 5 players on the bench. They don't have to equal each other. They just have to stay constant in time, right? So let's just do one other side note here. Let's say A is a solid. We have 2B, that's an aqueous. Equilibrium with 3C, that's a liquid, and then we'll go D, that's a gas, right? So that's how it's set up here. They're going to ask you for the KEQ expression. Even if later on I'm going to use ice tables and put numbers in, I would still start off using just the lettering in the KEQ expression. I just want to remind you, for a KEQ expression, because solids and pure liquids don't change composition, like I alluded to earlier, the KEQ expression will always ignore every solid. You can have 5 solids, ignore all of them. Ignore solids and pure liquids. I'll remind you again, a pure liquid is when is the only liquid, only L in the whole equilibrium, left side or right side. And it doesn't count here if there's a liquid and one aqueous, that's still the only liquid. So in this case here, solid, I'm not going to worry about it. Liquid, it's the only L in the entire expression. I'm also going to drop that, even though it would have been C cubed. Basically, I absorb it into KEQ constant. And basically now, KEQ, which is products or reactants, is just simply going to be D. Gases are definitely included. B, aqueuses are definitely included. The numbers go up into the powers, so B squared there. So it gives us that ratio. And then we started working on a few sort of ice table style questions here. For an ice table, sure, we'll use the same expression here. For an ice table, we use the balance equation sort of as the header. I just want to show you how an ice table would look like if I have things I ignored in the expression. Although there would have been numbers, like maybe I have a little bit of solid, maybe it does actually have a number, but because there is no change involved, it's like doing an ice table. ICE down the side here. I stands for initial. It stands for your beginning reading. C is your change. Remember, your change line is according to the mole ratio. Change line follows the mole ratio. And then we're going to end up with the E, which is our equilibrium. If I have a solid that I'm ignoring, basically just leave that column blank. I would just imagine that those numbers have been absorbed into KEQ. You're just tracking the changes. Maybe initially in your container, you just put in D, right? So I have a number here, let's say it's 10 molar, just for argument's sake here. If I imply that I have not actually added any B, I can assume that's 0. Sometimes they're going to give you one of the equilibrium numbers. Oh, by the way, B actually is this number here. That way, let's say the number was like 4. Then you can say, oh, this one here is actually gained by 4. If you know one of these numbers, you can just do a mole ratio. If one side is plus, I can't drop any lower than 0. The other side has to be minus. The change line has to follow the mole ratio. So if this went up by 4, when it's a 2-to-1 ratio, this one goes down by 2. That allows you to get to the 8. It's totally possible that you may have those starting conditions, A and 2B, 3C, and D. Let's start off with the same conditions. Let's start off with this one here being 10 molar. That's your initial line. Again, what I want to emphasize here is initially, it's totally up to you how much you put in. Just because this is a 1-to-2 ratio doesn't mean you have to toss in 10 molar and then you have to toss in 20 molar B because it's a 2 ratio. I just tossed in the D. Sorry, not D squared. No, I have a D squared there. You're just going to add chemical D here, which is 10. Notice I tossed in 0 in the first step. It's totally possible I may actually toss in, let's toss in 0 for the first step again. It's possible they don't give you any numbers for the equilibrium constant. In that situation there, what you would do, again, you can't drop any lower than 0. Again, it's obvious which side is plus. I'm going to go up by 2x. X is my unknown here. If one side is plus, the other side is minus. Whenever you have the I and the C row, you would just basically do the math here. 0 plus 2x is 2x. 10 minus x is 10 minus x. So be it, right? And then you would actually, whenever you have these placeholders here, you can sub them directly into the KEQ expression. The KEQ gives us that constant, gives us that ratio between how many products and how many reactants we have. Lastly, I want to just introduce to you here, just for some familiarity, let's just use the same equation. A and 2B are in equilibrium with 3C and D. It's possible that when I actually put into the container, it's possible I added in D and I also added in some B. Doesn't take a lot. Maybe I added in, let's say, 6 of D and 4 of B. Totally up to me how much I add in. In this situation, again, I can leave the A and C alone because I'd ignored those in the KEQ expression. This time, it's a little bit more uncertain which side is plus and which side is minus. So what we're going to end up doing, in a case like this, we're going to take the initial line, and what we're going to do is we're going to calculate. In words, we can say a trial KEQ. For short, you can just say Q. Basically, Q is also products over reactants. It's D over B squared, just like earlier. But it's using the initial values as opposed to KEQ, which always needs the equilibrium values. And what you're going to have is a couple of situations. If the Q that you calculated, with the random amounts that I put in, if the Q is equal to KEQ, we happen to luck out the system is already at equilibrium. There's no more shifting. What if my values currently, what if Q here, let's actually type it in, 6 divided by 4 squared, my number, based on my random numbers here, is 0.375. Let's say I was told the K is supposed to be, right, at equilibrium. I'm at a temperature where the K is supposed to be 2, right? So in that situation, my Q is actually less than KEQ. The KEQ is going to be a constant. The KEQ is going to stay fixed at a number 2. But for my number to go from 0.375 and start climbing, getting its way up to it being 2, I need to basically take my product over reactant ratio as it is, and I need to make this fraction bigger. For this fraction here to be bigger, I need to increase products, decrease reactants. I need to ensure that I have more products at the end. In that case there, the system, we actually shift right, shift to products, and therefore we have plus on the product side. So for my ICE table, when it wasn't as clear which side should be plus, which side should be minus, by testing this condition, because I'm not quite large enough on the product side, I then decided this side is plus, this side has to be minus. One side has to be plus, the other side has to be minus. If in contrast, I'm at a different temperature, if Q is greater than KEQ, so right now, currently my fraction here, it's too big for KEQ. For my number to actually shrink and get closer to my KEQ of 2, maybe my product needs to drop, my reactant has to increase. In that case there, to reach equilibrium, I actually need to shift left, and therefore we're actually going to have negative on the, positive on the reactant side. Okay. Especially when we deal with x's, remember we don't need to use a quadratic formula. They're always going to choose the number so nicely that you can just easily do a square root. So make a note to yourself. We don't need, or we won't need to use the quad formula. There's always another way around it. Okay. In this chapter, it was usually, I would start off with equal amounts that I put in, and you just square root it to get rid of the squares all at once. Gets rid of all the binomials, gets rid of any quadratic that you might need. All right. So that's just a quick overview of our chapter here. If you have any problems, just let me know. Thanks, guys.